Okay, I think we'll get started. So today we're going to be talking about charges, and it's about time we start getting into charges. We've used the idea in previous videos to set up potential energy and other things, but we're going to want to move towards a more formal understanding of charges. Now, we've already talked about the fact that there's a fundamental unit of charge, and that's sometimes called the charge of an electron. The electron carries a negative charge, so that's a convention that's been developed, that the charge that the electron carries will be considered negative. The proton carries an equal charge, but positive, so an equal but opposite charge. So there are these discrete units of charge, but when we're talking about a macroscopic object, like rubbing a balloon on your head and sticking it to the wall, we can essentially talk about charge as being a continuous quantity because the unit of charge is so small on the macroscopic scale. Now, the charge, though, is ultimately boils down to electrons. So if the object loses some electrons through, say, friction or other ways, then the charge will be positive, and if it gains electrons, then it will be negative. And that can build up pretty substantially, and we see this in most dramatically in clouds that build up a charge relative to the ground, and then ultimately we get a lightning strike. So this can be significant, even though we're talking about electrons here at the end of the day. All right, well, as we've already been talking about, so I'll just go through this pretty quickly. Like charges repel, whether it's both positive or both negative, and then opposite charges attract. And so we've seen there's an analogy to gravity, but unlike gravity, which has only the attractive force between two masses, the electrostatic forces add this extra layer in which we can have either repulsion or attraction. So it's important to note that. Now, we'll talk about conductors and insulators today. A conductor is one in which the electrons are free to move throughout the whole macroscopic system. Insulators are such that the electrons are stuck to their individual atoms and molecules. They can slosh within that, but they can't move throughout the whole bulk unit. So when we consider electrons, we can think about these. When we consider conductors, we can think about the electrons as being free to move anywhere on that conductor. All right, well, let's just take this in steps. Let's say we have a sphere, solid metal sphere, so conducting sphere, and let's just put two electrons in. Well, where are they going to go? They're going to be in antipodal positions, right? Doesn't matter kind of the orientation, could be any orientation, but for sure, they're going to want to get as far apart as possible, but they can't leave the conductor. It would take too much potential energy to leave that conductor. So they will get oppositely situated on the surface of the sphere, and they will be in a linear configuration, so a straight line. Well, let's dump another charge in and see what happens. What kind of geometry will that adapt? So again, they'll try to get as far apart as possible, and that will form a plane. Now that plane could be oriented in any way in space, but the 3 points will form a plane, and they will give rise to a trigonal planar geometry in space. Well, now let's add a fourth electron. Now here, well, okay, if we were stuck in 2 dimensions, then we would form a square, but we're free to come out into the 3rd dimension because this is a 3-dimensional solid metal sphere. And so the shape that will get the electrons farthest apart is a tetrahedron. So this will adopt a tetrahedral geometry. What we're trying to indicate here is that the center of the sphere and then 2 electrons form a triangle, and if this is the plane of that triangle, then this is the plane of another triangle formed by the other two. So they're the planes are perpendicular to one another. All right, let's add a, whoop, looks like we're missing an electron here. Let's add a fifth one. And what will this adopt? Well, it will adopt something called a trigonal bipyramidal configuration. So 3 will form a triangle in a plane, right? And that can be oriented any way we want. And then 2 along a line perpendicular to that plane, trigonal bipyramidal. And then finally, let's just add a 6th one, and that will form an octahedral configuration. So in one plane, there'll be a, well, in any plane, there'll be a square, and then we'll come out 90 degrees to that plane as well. Okay, well, let's add essentially an infinite number of charges. They're going to spread out evenly and form a spherical geometry on the surface of that conductor. So this is true of any conductor. It doesn't have to be a sphere. Any excess charge will be, or any excess electrons will move to the outer surface of the sphere. So the electrons are right on the surface of the sphere, and that allows them to get as far apart as possible from one another. Now we might say, well, what about plus? What about a positive charge? And say, okay, if we were thinking of positive and negative as completely symmetric, well, then the positive charges would just move out. But of course, when we go back to where these positive charges originate, they originate on the atoms. So we have to be a little more subtle here. We aren't moving positive charge to the surface. It's that we have a deficiency of electrons, and the electrons are free to move. So if an electron was here on this molecule near the edge of the sphere, or atom near the edge of the sphere, but there was an open, that would then mean there's an open positive somewhere that's not on the surface, and it would be more favorable for that electron to find that, so that the positive charges would be as far apart from one another. So even though there's an asymmetry in that the electrons, the negative charges themselves can move, in effect, the positive charges move in that the electrons can clear away that positive charge because the electrons are free to move. And so that's effectively the same as the positive charge moving. So the net result is if we have excess positive charge, then that will also be at the surface of the sphere. All right, well, let's imagine we've got some kind of conductor, and we said the charge is not moved to the surface, it's just throughout, but we have some excess charge on this conductor, and wherever that may be. And so imagine we've take like a plexiglass rod and rub it on a wool scarf or something. We accumulate a charge. So somehow we've charged this, and we'll bring it in proximity to a neutral sphere, okay? Or any kind of conductor. It doesn't have to be a sphere. And what will happen is electrons will move towards that positive charge. But as they move, they will leave behind this positive charge. Now, eventually, too many electrons will move over here, and they'll leave behind too many positive charges, so they would want to move back. Right? Well, it's not going to be this oscillatory motion. They're just going to move enough to appropriately be attracted to these charges while not leaving too much excess positive charge behind. So the stronger this is, the stronger that separation will be. Well, that's called a polarization. And this polarization then is macroscopic in that it's across this whole big conductor, something big enough that we could hold in our hands. And that's called electric polarization. Now, let's say we have an insulator in the same situation. Well, now the electrons are not free to separate like this. They're not free to move throughout. But each individual molecule that makes up this conductor, or this insulator, sorry, is polarized itself, just microscopically. So it induces a microscopic polarization. Now, there's a lot more to that, and we're going to actually not talk too much about these insulators, or also called dielectrics, in this course, although we will see them when we talk about capacitors. We will address them much more thoroughly in the third of the sequences of this Introduction to Physical Chemistry courses, when we talk more about the detail of electrical insulators and how polarization can develop. All right, well, let's talk for the moment, finish up here down at the atomic level. Now, we will, of course, go through this much, much more thoroughly, but to just begin with, we know atoms and molecules are made up of these charges, the protons and the electrons. In, say, a molecule of water, the electrons are distributed throughout this molecule, but there's an inherent polarization, always. We don't bring another charged object near it. It's inherently polarized, and that's called a permanent dipole. And that occurs oftentimes when we have some sort of asymmetry in the molecule. Now, we will learn very soon about why the dipole happens in the context of the types of chemical bonds involved. But for now, we just know that some molecules have permanent dipoles. Other molecules do not. Their electrons are evenly distributed about the whole molecule. Nitrogen is an example of that. But let's imagine we bring that nitrogen near a positive charge or a negative charge. That will distort those electrons around this molecule more so than it distorts, it'll just distort the electrons around and induce a dipole. So the presence of a charge can induce a dipole. Now, in either case, if we do have a charge present, if we have a permanent dipole, that can align, and we will talk carefully about the rotation of a molecule due to the presence of a charge coming up soon. But that can align so that in this case, water molecules are solvating this ion such that their negative sides of their permanent dipole are facing that positive ion. And this could also, although I haven't drawn it here, this could also happen for a molecule that only has an induced dipole. The charge, present of the charge, would induce the dipole, and that would orient around the presence of the charge. All right, so this is our first formal step looking at charges. We do need now to figure out what is the actual force between charges, and that's something called Coulomb's law, which we'll pick up in the next video.